Right, hello U11, and today we are going to be looking at two different factors that affect the rate of a reaction, and I've separated them out into two different parts. So we're going to start off with catalysts. So what do we need to know about catalysts? Well, we need to know what a catalyst actually is, so what we class as a catalyst. We need to know how it is that they speed up a reaction. And we also need to give an example of how they can be used in industry. So let's start with the question, what are catalysts? Now you will probably know from enzymes, which are a biological catalyst, that catalysts are substances that change the rate of reaction without being used up in the reaction. So that means they will speed up a reaction, but they're not actually taking part, they're not changing the bonds, they're not forming a new product. Okay, and that's really important because it means that we can use them over and over again. Okay, so that's what a catalyst is. You want to put that definition down, you might want to pause the video so that you can do that. Okay, so it's really important. It's a really important thing that we know about in industry because it can actually reduce the overall costs of manufacturing different goods. So quite a lot of reactions that we want to happen when we're making goods need to happen at a very high temperature or a very high pressure. Which is what you were looking at with Miss Slade yesterday. And to give very high temperatures and very high pressures, you have to buy specialist equipment. Obviously, you use a lot of fuel, so it becomes very, very expensive. So if we can use a catalyst, we can speed up the reaction, but not actually having to go to those high temperatures or high pressures. Now, catalysts are quite often the transition metals. So that is that block of metals in the middle of the periodic table between group 2 and 3, and we tend to use them in powdered form. Okay, and we can also use them in pellets, or we can actually attach them into a gauze so reactants can flow over them and come into contact with the catalyst. Now, why do you think that using powdered catalysts or pellets is the best thing to do? Pause this video and have a think. Okay, so hopefully we have linked in with another factor that affects the rate of reaction is surface area. So the finer something is, or the more broken down something is, the larger its surface. And we're going to be looking at surface area in the second part of this lesson. So how do catalysts actually work? So what catalysts do is they provide a route for a reaction, an alternative route, and that alternative route has a lower activation energy. So that means that when those particles collide, they don't need as much energy for a successful collision, for a successful reaction. So it means much more likely to react with each other. So that causes the reaction to speed up. Now you'll notice this energy profile diagram. You should recognize this from other topics, but you've got the reactants on the far left hand side, and then it goes up, bumps upwards, and that shows the amount of energy needed to start a reaction, and then it goes down as energy is being given off. Now you can see that without a catalyst, that activation energy level is much higher, so it needs a lot more energy to get the reaction going if there's not a catalyst involved. Whereas if we have a catalyst, you can see that it's using about half the amount of energy. Okay, so you're going to be doubling that rate of reaction. Now you need to know where examples of where this is used in industry, and it's used in a lot of things, but something that you will probably be familiar with is in a car. So what part of a car uses a catalyst? Do you know where there is a catalyst in your car? Okay, I'm sure many of you know that in the exhaust there is actually something called a catalytic converter. Okay, so this is part of the exhaust. It's before it reaches the outside world. There is a mesh that is made of platinum, rhodium, and sometimes palladium. Now, you probably recognise platinum being very expensive. So these catalytic converters are incredibly expensive and sometimes even stolen from the car so that they can use it and sell it off the platinum. Now, the reason that that is in there is because it converts the exhausts that are not very nice that come from our car. So it actually converts carbon monoxide, which is poisonous. It converts nitric oxides and hydrocarbons that haven't combusted into water, nitrogen gas, and carbon dioxide. Now, we've spoken about some of these gases in previous sections. So carbon monoxide we know is poisonous, so it's good to convert that into carbon dioxide. Nitric oxides we know cause things like acid rain, and is also a greenhouse gas, so we want to convert that. And hydrocarbons, if that will cause things like particulates, if they're not completely broken down, so we want to get rid of those things. So even in cars, they have got these special bits of equipment that try and lessen the damage that they are causing. Obviously, if they produce no fumes, that would be ideal. So there's a couple of pros and cons that are nice things to think about if you're ever asked about what advantages and disadvantages there are of using a catalyst. And we've covered quite a lot of them. I'm going to include some others that you might not have thought about. So good things about using catalysts, reasons for using catalysts in industry, is that they speed up the rate of reaction. That means you are going to make more product quicker, which means you're going to make more money. They're not going to be used up, so that means you can use them again and again. So it's not going to be this additional expense that you have to keep replacing all of the time. You actually only need a small amount, especially if you powder it up and put it into pellets to increase the surface area. You don't need vast amounts of the transition metal. Quite often gold is used as a catalyst. There's quite a few reactions that specifically require gold as a catalyst, and it's obviously going to be beneficial if you're not using huge amounts of very expensive metals. Some of the negatives, it can be expensive, so gold, for example, platinum, things like that. If you require a large amount of it, then it is going to be expensive. One catalyst will usually only work for a specific reaction. So the practical that I'm going to move on to in a minute, actually going to be looking at 3 different catalysts that catalyze the breakdown of hydrogen peroxide, but one of them is significantly better than the other 2. But quite often there's only one catalyst that will work. They are specific. Also, at some point they are going to need replacing. So that might be expensive if you're using metals like gold and stuff like that, but you don't have to replace it frequently because it's not actually used in the reaction. So what's going to happen now is going to cut to a video that I have recorded with Miss Donaldson, who is demonstrating, and we're going to look at how catalysts can affect the rate of a reaction. You do not need to write anything as we go through it. But what is going to be really important is the equipment that I'm using, because I'm going to be using a gas syringe, which is a far superior piece of equipment compared to what we're going to look at tomorrow. And also ways in which we can measure that rate of reaction. So I hope you enjoy the video and stay on afterwards where we're going to talk about surface area.
Right, okay, Year 11, welcome to our practical demonstration, which is looking at how these different catalysts are going to affect the rate of decomposition of hydrogen peroxide. Ooh! So hydrogen peroxide breaks down into water and oxygen, and we are going to measure how long, or we're going to time how long it takes to produce 50 millilitres of that oxygen gas. Now, tomorrow you're going to be looking at the method bubbling through a measuring cylinder, but today we're going to be using the much better method, which is this nifty little device called a gas syringe. Okay, it's going to give us a much more precise reading. Look at those graduations, and it's also going to give us a much more accurate result. So today we're going to use the gas syringe to measure our product formed, and we're going to time it so we can work out the rate of reaction. Okay, so I've now got my glamorous assistant who is measuring out 10 milliliters of our hydrogen peroxide. If you are using a measuring cylinder to do it, then there is a meniscus, which I will show you, as I'm able to on this one, which is kind of where it dips down, excuse the dog, dips down at the top level, and that is the bottom of that dip is where we take the measurement from. So Mrs. Donaldson there is doing a great job of measuring 10 mil, and that 10 mil of hydrogen peroxide is going to go into our conical flask. Okay, so it's called a conical flask because it has a conical shape to it. Very exciting. Now, the first of our 3 catalysts, which are 2 of them contain enzymes, is going to be celery, and then we're going to do liver, and then we're going to do manganese dioxide. So I've got the stopwatch here. Miss Donaldson in a second will put the celery in, and then we will time how long it takes to make 50 milliliters. So whenever you're ready, miss. Okay, now as you can see, it's a really exciting reaction, this one. Loads of stuff happening. And if you can't tell, I'm being incredibly sarcastic. So there is some bubbles that you might see it being formed. That is going to go up the tube. I'm going to stop the recording now because you will be very bored watching this till it gets to 50 mil. But you can see that it is starting to move the gas syringe. Okay, so I've made a very simple table. You do not need to copy this table. It's just to put our results on. So this is the formula, if you want to know, for hydrogen peroxide. And this is making water and oxygen. We've done our first one, which is celery. It took about 383 seconds. Our next one that we are doing is the liver. And the liver will contain enzymes. Celery will have the enzymes, but the liver will have more concentrated enzymes because the liver is really important at breaking down these poisons like hydrogen peroxide. So it's got lots of enzymes there to carry that out. So we need to put 10 milliliters of hydrogen peroxide into our conical flask. No pressure, Miss Donaldson. Doing a great job. I do appreciate this. I'm sure these guys will when they see what it's like tomorrow when I'm doing it on my own. That focus there to get exactly 10 mil. Brilliant. That's going into our conical flask. Just going to already reset. Thank you. So I've got my stopwatch ready, and whenever you're ready. Ooh. So you can see, even though this liver is frozen, and then we just defrost it for times like this, you can see that it's producing a lot more gas a lot quicker, and you can see that syringe flying away compared to the celery, which you did not have to sit through, unlike us. So it's gone past 40, 45 and 50. So that is 25 seconds. So we're going to set up for the next one. I'll pop that in my table, and we'll do the last one. Okay, so as you can see, we put in the liver result for 25 seconds, and we're now going to do manganese dioxide. So this one is not an enzyme containing enzymes like the other two. So let's see how that goes. So Miss Donaldson is putting the 10 millilitres of hydrogen peroxide. So we controlled the volume, we controlled the concentration, but I'm sure you probably realise we have not controlled the mass of catalyst that we're adding each time. So we're going to, let's get ready to see this. Add the manganese oxides, starting my timer. So you can see that is producing gas very, very quickly, so much so that, stop, there we go. So very, very quick reaction. Not sure how much detail you're able to see, but it's making this beautiful black sludgy liquid, and it's already gone past 100. So I'm going to take the lid off before that breaks. Right, so going to add the results. We'll find that, so 7 seconds on there. So as you can see, even though all of them did catalyse the reaction, the manganese dioxide provided the best pathway with the lowest activation energy needed for the reaction. So thank you very much, Miss Donaldson. No thanks to the dog. That is just annoying. And back to it.
Okay, so we're going to move on to the second part of the lesson, where we're going to be looking at how surface area affects the rate of a reaction. Now, the kind of thing that we need to know about is, what does surface area actually mean? How can you increase the surface area? And how and why does that change the rate of a reaction? Now, surface area is probably the one that students struggle with the most, because it's quite hard to picture in your mind, and a lot of students get confused between mass, so the amount of something, compared to the actual surface area. So it's not that we're reducing the mass, it's just that we can break it down and increase the surface area. So when you are in mass, if you are calculating the surface area of a cube, you know that you need to times the base by the height, and then times that by 6 to give you all the different surfaces. It's not a volume, so it's just all the different surfaces. Why is that important? Well, I'm going to put that idea into context. Okay, so I'm going to be using cubes in this idea, so please bear with me. So hopefully you realise that if I have a 1 centimetre by 1 centimetre by 1 centimetre cube, which is the one on the left, the small one on the left, the total surface area of that cube is 6 centimetres squared. Now, if I got 8 of those cubes and put them all together to make one bigger cube that was 2 by 2 by 2, the total surface area of that would be 24 centimetres squared. Okay, so ignore the first cube. I've now got 8 cubes, they're all together, so there's the same number of cubes, it's got the same mass as the next one, but they're all together, so they've only got a surface area of 24 centimetres squared. Whereas if I broke them apart, those 8 1 by 1 by 1s, if I broke them all apart, I would end up with 48 centimetres squared surface area. Okay, because you've got all of that surface in the middle that you couldn't count when they were all together. So it's really important to remember that with surface area, it's not that something is smaller, that it's got less mass, there's less of it. It's just that it's broken down. Okay, so if I took a big rock, okay, and I broke it down into smaller rocks, I'd still have the same amount of rock. So if I put it on a balance, it would still give me the same amount of kilograms, but it would have a much larger surface area because it's all broken down. Here is another picture that might help you picture it. So if we look on the left-hand side at A, we've got the same number of blue particles as we do as B, but they're all together. So that has got a smaller surface area compared to B. In B, it's all been broken down. That means that there are a lot more particles exposed to the red dots, the reactants. Okay, so it means there's more particles exposed. That means they're more likely to collide. And that's really important. I've got to say, why does increasing surface area increase the rate of reaction? Because there are more frequent or a higher number of successful collisions. Okay, so if you break something apart, it means there's more particles there that are more likely to collide. Okay, I always used to use, so some of you might have already heard it, if you're in the Arctic and you had a machine gun and you wanted a penguin sandwich, if you come to a big group of penguins all gathered together and shot your machine gun, you'd only be able to pick off the penguins on the outside. So if you wanted a massive penguin sandwich or to feed a huge amount of people, you'd fire your machine gun up in the air first, let them scatter, and then use the machine gun to get all of them. If that helps, I hope that it does. If not, please forget that analogy, especially if you love penguins, which I do. Please do not go and shoot penguins. Okay, so I'm going to go now again to a practical that is going to be demonstrated by Miss Donaldson, and I'll talk our way through it. So we're going to be looking at surface area, and we're going to be looking at the surface area of calcium carbonate. So I've got 3 different forms of calcium carbonate that changes the surface area. We're going to react it with the same concentration of hydrochloric acid, and we're going to measure how long it takes to produce 50 milliliters of gas again, or 50 centimeters cubed of gas again. So I hope you enjoy that. After that, that will be it. So I hope you have a lovely day, and I hope that today has helped.
Okay, hello Year 11, and welcome to the second practical, where we are going to be looking at the effect of surface area on the rate of reaction. Now, weirdly for you, this is our last video because we realised, looking back through all of the videos we made, that we were actually on mute for the first 2. So here is a table of results that I lovingly and beautifully described as we went through, showing the increasing surface area. So from the large chips that look like this to the small chips that are that size, and the powder. Now the best one is the powder, and don't worry because that one for some reason wasn't unmuted, so after this it's going to skip to that one. But I'm just going to re-record this bit. We're just going to do the larger chips again, just so you can see what is happening, and I'm going to explain what I've done here so that you can follow along. Okay, so we've got very similar equipment to the catalyst one, and I've got my glamorous assistant and dog playing in the background again. So Miss Donaldson has measured out 10 milliliters of 2 molar hydrochloric acid. So we are controlling the volume and we are controlling the concentration of the acid. Miss Donaldson has also weighed out some large marble chips because we also want to control the mass. So we have made sure there is 0.03 grams of calcium carbonate every single time. Okay, so marble chips are made of calcium carbonate. So we've used 0.03 grams calcium carbonate each time. Okay, now because we are able to control a lot more factors, a lot more variables than the last one, it means that we're actually going to use these results to calculate a rate of reaction. So I've got my trusty stopwatch here. Miss Donaldson is ready with the chips. These are the large chips, so these will have the smallest surface area. They are in. It is beginning. Does anyone know what the 3 products will be from calcium carbonate reacting with hydrochloric acid? Quickly, think to yourself. Well done if you know it will be calcium chloride, water and carbon dioxide. And it is the carbon dioxide being produced that we are measuring. So we have got, again, our very accurate, very precise gas syringe, and you can see that it is slowly moving along. Okay, now light blue Peter, here's one I did earlier, or we did earlier, and we can see that it actually took 109 seconds for the large chips. Okay, so what we're going to do is work out the rate of reaction. So that is centimeters cubed per second. So I can take the amount of gas, the volume of gas being produced, which was 50, divided by the amount of time, 109, and that gives you 0.46. Okay, skipping ahead, we did exactly the same, and it was beautifully videoed, by the way. For small chips, Miss Donaldson measured out 0.03 grams, and it took 50 seconds. Don't need a calculator for that, because anything divided by itself is 1, but I still have to put 0.00 because the other ones are to 2 decimal places. The last one, which you will actually see the video for, is the other extreme compared to this one, which is very, very slow, is going to be the powder. And what's important to know is that these large chips, even though it's large chips, they've got a smaller surface area, okay, because they're not broken down. So apologies that you missed the middle one, but that was the magic of the first. It's just gone past 50 anyway, but we've used the last results anyway. So the next one will be the powder. Okay, so we're now going to look at the final one, and I've added it onto my table, which you do not need to copy, but if you wanted to, that's absolutely fine. Just to make sure that you're happy that the surface area increases as we go down this table, so the powder has a much larger surface area compared to the large chips. Now, Miss Donaldson is very carefully, as you can see, tapping out the powder, trying to get it bang on 0.03. She's done it. Well done. So we've got the same mass, but this is a fine powder, so it's going to have a much larger surface area. We have got our 10 ml of hydrochloric acid measured out, which goes into the conical flask. And where's my stopwatch, because it's going super quick. Now, sometimes this happens, you can't actually record it, but we'll give it a go. Okay, really quick, Mr. Like, in and stick on that bung.
Oh my God.
There we go. Take the bug out. There
Jesus.
We go. Okay, so really quick, excuse that profanity there. So we can see from here it's 0 point, it's 2, that's pretty much 3 seconds. So we'll round that one to 3 seconds. Okay, so if we're doing the same equation, it's producing 50 centimeters cubed in 3 seconds. We just need to do the 50 divided by 3 gives us 16.6 recurring. So to 2 decimal places, that would be 16.67. Okay, so you can see as the surface area increases, the rate of reaction has also dramatically increased. Okay, and why does that happen? Because there are more particles exposed, so there are more collisions, or more frequent collisions. So thank you very much for joining me in today's lesson. Thank you to Miss Donaldson for demonstrating on this, and we will be back with you tomorrow, where you get to see me using the camera on my own, and it all goes horribly wrong. So thank you very much, and goodbye.